Welcome to OOTO TV, the out-of-the-office investigation from the past into the future of marine navigation and autopilot technology. This time we're discussing requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation. I'm General Cromwell.
And I'm Commodore Hazard Perry. Today, Cromwell, we are charting a course into an incredibly complex but, absolutely vital topic. We're going way beyond just looking at a GPS screen. We're actually investigating the rule book itself, that foundational document that's going to dictate how the next generation of tools will safely guide these giants of global trade across our oceans.
And the scale of this it's staggering, Hazard. We're talking about the technological backbone that supports pretty much all of global commerce. I mean, over 90% of everything in the room with you right now, your phone, your clothes, the coffee you had this morning, it all spent a good chunk of time on one of these vessels. It did, exactly. And for that journey to happen safely, the human navigator on the bridge is relying on a suite of tools that are getting more integrated, more complex, and more indispensable every single year. The economic and environmental stakes are just astronomical, and that margin for error, it's shrinking to basically zero.
This quote from Captain MacArthur really just hammers home those stakes. The Ever Given? That wasn't a malicious attack or anything. It was a really complex navigational incident, with weather and human factors all mixed in. But look what happened. It held up about 12% of global trade and cost billions. It showed us all just how fragile these critical arteries really are. Oh, it's a crucial reference point. It completely reframes our investigation today, because if a simple accident can do that, just imagine the potential impact of a system that is deliberately compromised. We're not just trying to specify a better map here. We are architecting a system of trust, one that's engineered for resilience in a world where these systems are becoming targets. So to structure our analysis, we've laid out 5 key sections. We've kind of touched on the high-stakes compass, why this all matters so much. Next, we're going to move to the bridge itself with designing for the helm. Then we'll go under the hood to explore the unseen signals and the really profound risks they carry in guarding the ghost signal. And finally, we'll look out to the horizon with navigating the future. Okay, let's get right into the specifics. To build the blueprint for this ideal navigation tool, the absolute first principle, the starting point for any requirement specification, has to be the human at the helm. I mean, all the sophisticated tech in the world is useless or even dangerous if it's not designed for the person who has to use it under immense pressure. That's so right, Cromwell. And to do that properly, you have to build upon a really structured foundation.
You see, the requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation, it has to be clearly defined in a step-by-step manner to meet 3 primary categories. First up, audience needs. Who is actually using this thing, in what conditions, and what information do they need at a single glance? Second, you've got the technical requirements. What does the hardware and software really need to be capable of processing and showing? And third, safety and regulations. What are those non-negotiable international rules and built-in fail-safes we absolutely must stick to? You just can't compromise on any of them.
And the modern nexus for all of this is the Integrated Bridge System, or IBS. You should really think of it as the ship's cockpit and central nervous system all rolled into one. Decades ago, you'd have this collection of separate, standalone instruments, but now the IBS brings radar, electronic charts, GPS, depth sounders, the autopilot, everything into one cohesive, interconnected workstation. The whole goal is to give the officer of the watch complete situational awareness from a single point of command. This block diagram really brings that central nervous system you mentioned to life, Cromwell. You can see all the different sensor inputs, the gyro compass for heading, GPS for position, radar for contacts. They're all feeding into a central network and processor. That processor then drives the crucial displays, like the electronic chart, the ECDIS. But this brings us to the core question of this entire section. How can marine navigation and piloting systems for both inshore and offshore global navigation provide a high-quality experience for the user?
That really is the multi-million-dollar question, isn't it? It's not just about having the data, it's about presenting it effectively. This is where ergonomics and human-machine interface design become absolutely paramount. Classification societies have entire volumes of rules just on this. It's about logically grouping controls by function. You don't put the controls for the ballast pumps right next to the ship's horn. It's about making sure that in a developing situation with alarms ringing all over the place, the information is unambiguous and the controls are intuitive. A poorly designed interface is basically a latent hazard just waiting for the right circumstances to call a disaster.
Okay, so we've established that the user interface is an absolute priority. But what's feeding that interface? Now we need to peel back that layer and look at the fundamental technology that makes it all possible. We're moving from the screens the navigator sees to this invisible world of radio waves that connect the vessel to positioning satellites and to the rest of the world. This is really the bedrock of physics and engineering that the entire system is built on.
And this slide brilliantly illustrates the whole spectrum of tools that are available. It's not just one signal. Way down in the very low and low frequency bands, those really long wavelengths can travel for thousands of kilometers, literally hugging the curvature of the Earth. That's home to terrestrial systems like L'Orient-C, which serve as a vital backup to satellite navigation.
Right, and then as you move up that spectrum to VHF and UHF, the waves get shorter. They can carry much more data, but they're generally limited to line of sight. This is where you find your ship-to-ship radio for AIS, which transmits vessel ID and position, and crucially, those extremely high frequencies used for satellite communication. A truly resilient navigation system has to be multilingual. It has to be able to speak and listen across many of these different bands all at the same time.
So, Hazard, that brings us to the next critical question. Looking at this entire spectrum, what are the key technical elements for the requirements specification for marine navigation and piloting tool for both inshore and offshore global navigation? Well, Cromwell, while there are a ton of components, the undisputed heart of any modern system is the Global Navigation Satellite System, or GNSS. And the most famous of those is, of course, the American Global Positioning System. The entire system's sense of place and time, it literally beats to the rhythm of atomic clocks orbiting high above the Earth.
And this is where it gets truly elegant. This slide shows the genius inside the GPS signal itself. It's not just some simple tone. The satellite transmits a pure carrier wave, but then it overlays multiple complex data codes on top. You can see the standard CAA, or course acquisition code, that our civilian receivers use, and then there's the more precise P code for military applications.
But what makes those codes so special? Why are they the key to the whole thing?
Well, they are pseudo-random noise codes, or PRN. Each satellite broadcasts its own unique code. It's a complex digital pattern that seems random but is actually perfectly predictable. Your receiver on the ship knows the PRN code for every single satellite. It generates its own copy and virtually slides it back and forth in time until it perfectly aligns with the signal it's getting from space. The tiny amount of that time shift, you multiply that by the speed of light, and that gives you the exact distance to the satellite. It's this incredible symphony of timing. And when you get a lock on 4 or more satellites, your receiver can calculate its position in 3 dimensions with just phenomenal accuracy.
You're listening to OOTO TV with research by author Paul Bulow. So that symphony of timing gives you a precise position, but a truly modern navigation tool has to put that position into a rich context. To do that, the requirements specification for marine navigation and piloting tool for both inshore and offshore global navigation has to incorporate all these existing databases of charts, maps, passages, channels, obstacles, depths, traffic, weather, and it has to update the maps and course in real time using satellite feeds and all the data from the boat's own sensors, GPS, depth, speed, currents, fuel, and the desired course and ETA. It's a massive data fusion problem, which leads to a really fascinating forward-looking question, Cromwell. Can we connect to both Starlink type of satellite systems and use library data to relay time-updated new geographic region and new weather data for this tool? Oh, that is absolutely the next frontier, Hazard. Just imagine the bandwidth. Instead of getting these compressed, low-resolution weather updates every 6 hours, you could download entire high-resolution meteorological models in real time. You could stream live satellite imagery of ice fields up ahead, or get HD video from a pilot boat before it even comes alongside. The ability to pull huge data sets from the cloud via low-latency broadband is going to completely transform the predictive capabilities of these systems. It has to be a core requirement for the next generation.
But Cromwell, this increasing reliance on these invisible, complex signals from space, it introduces an entirely new class of risk. For every bit of accuracy we gain, we create a new potential vulnerability. And these aren't just technical glitches, these are critical threats that have to be addressed through robust safety regulations and system design. We have to learn how to guard these ghost signals. General Cromwell, Captain MacArthur's warning comes back, but here it's even more pointed. GPS spoofing is not a theoretical problem. It's been documented in multiple global hotspots. State actors and other malicious groups have demonstrated the capability to manipulate these signals, creating false positions for vessels and for aircraft.
This forces us to pivot from the incredible promise of the technology to the very real and present perils it creates.
And it is so crucial to understand the difference between these two threats. Jamming is a brute force attack. As the slide shows, it's really just overwhelming the weak satellite signal with a blast of noise. The GPS receiver loses its lock, an alarm sounds. The navigator knows immediately they have a problem. It's a pain, but you know it's happening.
But spoofing is deception. It's so much more insidious. A spoofer broadcasts a counterfeit GPS signal that's just a little bit stronger than the real one. The ship's receiver latches onto this false signal, and the navigation system confidently reports an incorrect position. The autopilot, trusting its primary sensor, will then diligently steer the vessel based on this lie, potentially toward a sandbar, another ship, or into contested waters. The system isn't blind, it is literally hallucinating.
So given this vulnerability to hallucination, how do we build resilience? Well, the answer isn't a better GPS. It's redundancy and independent verification. The cornerstone of this whole philosophy is the GMDSS. This isn't a single box. It's an internationally mandated framework of equipment and protocols. It ensures that no matter what happens to a vessel's primary systems, it has multiple independent ways to communicate and receive critical safety information. It's the ultimate safety net.
And this is a perfect example of a system within that GMDSS framework. Navtex. It's a simple, low-frequency radio service that automatically broadcasts vital safety information to ships. As the diagram shows, authorities like Coast Guards send out navigational warnings, storm alerts, and other critical data. The key here is that it operates completely independently of any satellite system. So if your GPS is being spoofed and telling you you're in the middle of a channel, a Navtex message might be printing out on the bridge warning you of a new unlit buoy directly in your path. It's a low-tech, but incredibly valuable reality check.
This brings us, finally, to the future. All of these requirements we've talked about, for intuitive user interfaces, for multi-layered signal processing, for robust safety and redundancy, they aren't just about improving navigation for human crews. They are the essential building blocks for the next great leap in maritime technology, the autonomous vessel.
Exactly, Hazard. You simply can't have an autonomous ship until you have a sensory and regulatory system that it can trust implicitly. We're laying that groundwork right now.
And this isn't science fiction. It is already happening. This timeline shows the rapid progression. The container vessel Yara Birkeland in Norway is already operating autonomously on short coastal routes. By 2025, which is just around the corner, we expect to see ships being remotely controlled from shore-based operation centers, at least in coastal waters. The evolution away from a full crew on every single vessel is gradual, but believe me, it is happening now.
But that rapid evolution brings a significant note of caution, Cromwell. This is precisely why the requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation are updated and evaluated on an ongoing basis. We have to incorporate needs and desires for new features and benefits and changes to existing regulations and requirements for marine travel. A specification written just 5 years ago would be dangerously obsolete today. With every new feature, like remote control, you introduce a new attack surface, like a cyber attack on the control link. The requirements document has to be a living, breathing thing that evolves just as fast as the technology and the threats.
You're absolutely right, Hazard. And that complexity is just compounded by the factors on this chart. The idea of a single, universal specification is a total fantasy. The requirement specification for marine navigation and piloting tool for both inshore and offshore global navigation vary by region, size and type of vessel, and local laws and situations, weather, events, and tradition. The requirements for a massive LNG tanker transiting the heavily regulated waters of the English Channel are worlds apart from those for a fishing trawler in the South Pacific. The specification has to be adaptable to an incredible diversity of vessels and operating environments. So, let's bring our own investigation to a close and try to synthesize what we've covered. We've journeyed from the critical human operator on the bridge, down into the physics of pseudo-random noise codes, through the insidious threat of spoofing, and finally, all the way out to the autonomous horizon. It really does boil down to these 4 principles. First, human-centric design. We saw that no matter how brilliant the technology is, it fails if the interface is ambiguous or confusing in a crisis. Second, layered technology. Modern navigation isn't a single device, it's a deep stack, from fundamental radio physics all the way up to cloud-based predictive weather models. Third, resilience through redundancy. In a world with threats like spoofing, the safest system isn't the one with a single, perfect sensor, but the one with multiple, independent backups, like Navtex that provide that crucial reality check.
And finally, constant evolution. As we race towards autonomy, the rules, the risks, and the requirements themselves have to adapt at the same pace as the innovation.
Which leaves us with this final, and I think really thought-provoking question. We spent this entire investigation specifying a tool, a system that is taking on more and more of the cognitive load of navigation. So, as we engineer these incredibly intelligent systems, as the ship itself becomes the navigator, what becomes of the captain?
Right. Does the role shift from a hands-on operator to a system manager? Maybe a mission commander overseeing a fleet from a control center on shore? Or do we risk engineering out the invaluable, unquantifiable human intuition and experience that has guided mariners for centuries? That, perhaps, is the most important requirement of all to consider for the future, and it's one that technology alone can't answer.